Hello and welcome to this lecture. In the previous lecture, we looked at multiple random variables, how to describe the joint distribution of multiple discrete random variables. In particular, I gave some simple examples of joint PMF, and we looked at the scenarios and computed what the joint PMF will be. Okay. Now we're going to start looking at marginal PMF. I sort of ended at in the previous lecture by saying when you have a lot of random variables, the joint PMF can become a very complicated object which you can't easily describe. So you're looking for some simpler alternatives, and this marginalization and conditional distributions are very nice pathways to get to the joint distribution. Okay. So let's start by looking at the marginal PMF. In particular, the individual marginal PMF is what I will start with, and then we will slowly generalize this. Okay. So we're going to look at multiple discrete random variables. We also we already saw the marginal PMF in the context of two random variables. Now we are going to increase the two to multiple. That's it, nothing more. Okay. So let's say you have n random variables, x1, x2, xn, and these are distributed with some joint PMF f sub x1, x2, xn, right? So something. And then the PMF of the individual random variables are these individual marginal PMFs that we are interested in, x1, x2 to xn. Okay. And we can quite easily see that the PMF of x1 itself evaluated at some t, okay, is going to be basically probability that x1 equals t, right? And it turns out you can find these marginal PMFs by summing over the joint PMFs for different ranges. What do you sum over? You basically sum over all that you do not want to keep. Okay, so if you're looking at fx1, you have to sum over everything other than x1. Okay, so the joint PMF of course will depend on x1, x2 all the way to xn. So you sum over the joint PMF. You can see here in the first formula there, fx1 of t, I'm summing over t2 prime, which is in the range of x2, t3 prime, which is in the range of x3, all the way to tn prime, which is in the range of xn. What am I summing? I'm summing the joint PMF evaluated at t, which is the value of x1, which I want to keep. So I won't be summing over t, I want to keep that t, and then everything else is all possible values. Okay, so this is a very simple proof. The proof is very similar to what we did before. Basically, I'm saying I want the probability that x1 equals t. I'll write the event x1 equals t as x1 equals t and x2 equals t2 prime and x3 equals t3 prime and so on, and simply add up over all possible values for t2 prime, t3 prime, t4 prime and all that. So that's exactly what it is. It's a very simple formula, except that when you execute it, sometimes it can become a bit confusing. But keep this rule in mind. Okay, when you marginalize everything that you don't want, you keep only what you want, you get the marginal PMFs. Okay, so when you go to x2, what will you do? You will keep x2 alone and then put variables for all the other random variables, sum over all of them, you get the marginal PMF of x2, so on. Okay, so that's the multiple discrete random variable marginalization. Okay, so let's see a few examples. As before, we've always been seeing examples. Okay, so let's look at an example. I'm going to toss a fair coin thrice. It's a fair coin, and x1 is the indicator for the first toss being heads as usual. x2, x1, x2, x3 are 1 and 0 for the first toss, second toss, third toss respectively. We've seen the joint PMF before. This is just 1 by 8. If you want to look at the marginal, say fx1 evaluated at 0, notice what I'm doing here. I'm keeping the 0 fixed. So let's maybe use some of the color here, blue. Okay, I'm keeping the 0 as x1 throughout. Okay, and the other guys are varied across. You marginalize it out. So you look at these guys. It's 0 0, 0 1, 1 0, and 1 1. All possible values. I just sum over all of them, and they're all 1 by 8. So 1 by 8 plus 1 by 8 plus 1 by 8 plus 1 by 8, you get 1 by 2. Okay, the same thing for fx1 of 1, and you get you sum over all these things. So you keep one fixed for x1, and everything else you vary, and you simply add it up, you get half. Okay, so it's easy enough. Okay, hopefully this is easy enough to execute. So this is a very simple problem, and you see how the marginals work out. If you do x2, also you'll get the same answer. x3 also you'll get the same answer. Of course, we knew the distribution of x1, x2, x3 before. It's not very difficult to do this. Okay, let's go to our slightly more interesting example of this 000 to 999 X is the first digit from left, Y is the number modulo 2, and Z is the first digit from the right. Okay, so in this case you might say, okay, I'll have to sum up over all the joint PMF, but really the marginal is directly and easily you can write it down. There's no need to sum over the joint PMF or anything. If you look at the first digit from the left, what's the probability that the first digit is going to be equal to 0? What is the probability that it's going to be equal to 1, etc.? You'll see all of them is 1 by 10, right? There are 100 out of the 1000 cases which are favorable for every particular first digit, right, from the left. If you want the first digit to be 0, you have 000 to 099. Okay, so that's 100 favorable out of the overall 1000. So you get 1 by 10. So it's easy to quickly see that X is uniform from 0 to 9. So you see, quite often to find the marginal PMF from an experiment, you may not have to do the summation and the marginalization very painfully. Directly you may be able to deal with the marginalization. Okay, so that is something that's important to remember as well. Don't go finding the joint PMF all the time. You may be able to quickly directly find the marginal. Okay, likewise Y is the number modulo 2. Okay, so Y is going to be 0 if the number is even and 1 if the number is odd. Okay, and exactly 500 out of these 1000 numbers are even, the other 500 are odd. Okay, so if you only care about even or odd, it's going to be uniform in 0, 1, right? So it's 500 by 1000, so it's uniform in 0, 1. Same thing with Z, right? Z is going to be uniform 0, 1 to 9. It's the last digit, the units place digit, that's also uniform from 0 to 9. So quite often the marginal may be actually quite easy to find. You may not have to worry too much about adding up over the joint PMF and all that. Okay, so let's come to this very interesting case. We've been talking about data a lot and practical examples, more complicated examples where the space is difficult to specify and all that, and this IPL power play over 1, the first over of the power play, is maybe a good example of such a situation. Okay, so we'll assume that this over has 6 deliveries. There are cases where it has 7, so let's say we just forget about the 7th delivery. We'll just consider the over to be the first 6 deliveries that are pulled. There's always be 6 deliveries in the over, so we do that, and xi is the number of runs scored in the ith delivery. Okay, so that is the variable. We've been looking at it. Now, what do I do for the marginal distribution of xi? So if you remember, I gave you this example and I said the joint PMF of x1 to x6 looks formidable to calculate, right? It's formidable to not just calculate, even specify or write down or think about. It seems like it's all over the place. You may not be able to really do something very clear, but you will see, interestingly, you can do something very reasonable for getting the marginal PMF of the x1 to x6. It's not too bad. Okay, like I mentioned, there are about 1500 IPL matches that have already happened, 1598, and if you tabulate the data from there, it's not too unreasonable to think of the marginal distribution of x1. So let's see, let me just show you how this works. We've seen before that you can take xi to belong to the set 0 to 8. It's very unlikely that more than 8 is going to happen. The trick is how to assign probabilities to these values, right? How do we do this? We have never done something like this before, isn't it? Previously, it's always been some toy experiment. We've been able to always, sort of figure out what the probability should be. And, how do you assign probabilities? Maybe you can guess from your experience of IPL matches, what is going to be the most probable run scored, let's say in the first ball. Mostly the batsman is going to defend or something, right? So in the first ball, x1, it's very likely that the 0 is the dominant number. In fact, you may even guess that 0 would be the most probable run that somebody scores of a delivery, right? Most cases, maybe it's 0. Okay, but boundary can happen. But how do we assign probabilities? What is a meaningful way to assign probability? So traditionally, what people do, this is again, this is probably not the best method, and but it's a reasonable method, and it's not too bad. Okay, so you can go out and collect the data in the past occurrences. So there's been, like I said, 1598 matches where the first over has been bowled so far, and you go and see in ball 1 what happened, as in how many times 0 runs were scored. And so it turns out in 957 matches 0 runs were scored. Look at the large fraction, right? and 1 run was scored in 429 matches. Together that covers a large variety of, large number, a significant number. And then you have 2 runs in 57 matches, 3 runs in 5 matches, and 4, boundary seems to be more popular, right, 138 matches, and then 5 runs in, 8 matches, 6 runs in 4 matches. That's it. So far looks like nobody has bowled a no ball and been hit for a 6 in the first ball, right? So you don't have 7 or 8. So one of the ways is to assign probabilities in the same proportion as data, right? So maybe you want to say probability that x1 equals 0 is 957 by 1598. I'm not claiming once again that this is the best way or anything like that. There's nothing like the best in these kind of things. It seems reasonable, right? And there are good reasons why this might be okay, and we'll see later on why this might be a good way to assign these kind of probabilities. But let's, and at least intuitively, most of you would say yes, that seems reasonable. Okay, so you can do that. Now you can repeat this for ball 2. So notice how these numbers are large enough. I would have liked to have 15,000 matches. Then maybe these numbers all will be much better. Okay, and but somebody might say, there's been only 4 matches where 6 was hit, but there's been 1,500 matches, and I'm looking at only 6 possibilities. So it's okay. It seems like I have enough data. It feels like I have enough data to make this statement. I'm making a lot of loose statements here, but these are important things to just think about. I've seen enough matches to be able to comment about what happens in the first ball of an over. It's not very unreasonable. Okay, so I have done this now. I've taken all the balls, the first balls. I've tabulated in how many matches 0 runs were scored, how many matches 1 run was scored in the first ball, second ball, third ball, etc. And I've put down the distribution in this little table here. Okay, so you can see the marginals one is able to think of in a reasonable way. Okay, so maybe I want to assign a probability of 0.5989 to x1 being 0. Okay, I want to assign a probability of 0.2685. This is again in proportion of how many times in the past this has happened. So maybe going forward, this is a reasonable way to assign the probabilities. And you can notice there are some subtle differences, right? For instance, a 6 is much more likely, some 6 to 7 times more likely to be hit off the third or fourth ball. Okay, the fourth ball seems to be very interesting for hitting 6, right? And you can also look at boundaries. Again, the fourth ball is much more likely than anything else. So in general, it seems very interesting, and it looks like 0 is lowest in the last ball. So almost for the highest time or proportion of times, 0 is unlikely in the last ball, but still more than 50% of the balls are dot balls, right? That's an interesting observation as well. Only for half the time across the matches, people hit it for runs. Okay, so you notice. I'll keep coming back to this example over and over again this week and in the next week also. This kind of a thing is very important for data science, and seeing the connection between where the probability distribution is coming from, where statistics will eventually come from, and then at least where data is entering the picture in terms of coming up with something. And I also want you to think about how if you want to look at the joint PMF for all the 6 balls, 1598 matches is not good enough. There are just too many cases, and they all won't appear even one time, or you can't really put anything down there meaningfully. I'll come back and comment on it for you later on as well. But at least this much we are able to do. The marginal with this kind of data we are able to easily write down. So maybe the marginal is a good idea. So let's see what else we can do with this data going forward. Okay, so what is the moral of the story? Moral of the story is, in large problems when there are a lot of random variables, marginals are your only way in which you're going to make progress. Okay, so you can't deal with the joint PMF. You have to look for smaller distributions and try to stitch them together, and how we do that we will see in this lecture. Okay, so let me now generalize a little bit. Okay, this is also important. Let's say we have 3 random variables now, and they have a joint distribution f x1, x2, x3. Okay, so I'm taking a very simple case. Just know we saw n random variables and all that. Let's just start with 3, right? After 2, we should go to 3. So we go to 3. We've discussed individual marginal PMFs, right? So we've seen fx1, fx2, fx3. Now, what about fx1, x2? Okay, this is the joint PMF of x1 and x2. It's a very reasonable object, isn't it? So just now I mentioned how the joint PMF of everything might be difficult, but what about joint PMF of x1 and x2, right? It doesn't seem that bad, and it's a very valid object, and can we say something about that? And likewise x1, x3, x2, x3, okay? So there is some meaning in this, and it seems reasonable to think of these pairwise distributions, for instance, when you have 3 random variables and not just the entire joint PMF. So it turns out this is very much possible, and you can do it exactly like before, the principle being when you want to marginalize, keep only what you want and sum over everything you don't want. Okay, so that's the principle of marginalization, isn't it? So if I want x1, x2, right, I want to find the joint PMF of x1, x2. I'm given the joint PMF of the whole thing. Let's say f x1, x2, x3 I have, right? I'm trying to marginalize and find f x1, x2. How do I do that? F x1, x2 of t1 comma t2 is the probability that x1 equals t1 and x2 equals t2, and simply you add over all possible values for x3, you're going to get this guy, right? So that's the formula that's given there. Sum over all t3 prime in the range tx3, the joint PMF t1, t2, t3. So given the joint PMF, you can always go to the marginals, right, in this fashion, and the marginals need not be individual random variables. They can even be pairs of random variables, x1, x2, x1, x3. What do you do for x1, x3? You sum over t2 prime, which is which will be this variable that is in the range of x2, tx2. You sum over all possibilities for x2. You will get fx1, x3. Same thing with x2, x3. You sum over all possibilities for x1. Right? So it's very simple extension, right? So we started with the entire joint PMF, and then we said maybe the marginals are interesting. We looked at the individual marginals. Now we have pairwise marginals, and you can now extend to other situations. Okay, so basically this principle is important to remember. Whenever you want to marginalize, you keep what you want, sum over everything you don't want, and you get a marginalization. Okay, so here's example. I mean, this is a simple enough example so that I can do this for you. So if you do x1, x2, right? So let's first marginalize somewhere here over f x1, x2. I'm going to have t1, t2, right? T1 takes value 0, 1, and t2 takes value 0, 1. Okay, so if you want to do f x1, x2 of 0, 0, so this guy, right? What will this be? So maybe I should use different colors. So I'll use blue. Okay. So 0, 0 is blue. So you have 0, 0 here, 0, 0 here, 0, 0 here. Okay. And T3, I have to sum over all possibilities for T3. Okay. So if I do that, I have to add 1 by 9 plus 1 by 9 plus 1 by 9, and that will be just 1 by 3, isn't it? So let's change color to look at 0, 1. If I look at 0, 1 would be x1 equals 0 and this guy, this position, and that is 0, 1 and 0, 1, isn't it? So you fix t1 to 0, t2 to 1, and then sum over all possible values for t3. There's only 1 and 2. Okay, it's 1 by 9 plus 1 by 9. I'll get 2 by 9. Okay. Let's change to some other color, it's orangish color. For 1, 0, so you have 1, 0 here. Okay, that's again 1 by 9 plus 1 by 9, that's 2 by 9. And then one can change to, I don't know, magenta or something like that for this 1, 1. And that's again another 2 by 9. Okay, so this is my joint PMF f x1, x2. Okay. So one can do also other joint PMFs. Let's say you want to do, I'll just do one more. Let's say we do x1, x3, okay, just for variety. You have t1 here and t2 here. Remember now t2 can take 3 values, okay. So t1 is just 0, 1, this is 0, 1, 2. Okay, so you have 6 possibilities here. I'm not going to bother with the colors, okay, bear me for that, okay, bear with me for that. So I want x1 0 and x3 0, okay, so 0, 0, okay, so maybe the first one alone, let's look at this in black. So this is 0, 0, that's it, that's the only possibility, okay. So x1 is 0, x3 is 0, it's just 1 by 9, okay. So x1 is 0, x3 is 1, is 0, 1, that can happen here, that's 1 by 9, 1k is 0, 1, Okay, so you got 0 1 here, 0 1 here, that's it, 2 possibilities, and that's 2 by 9. Okay, what about 0 2? 0 2 is, okay, 0 2 is out here, it's out here. Okay, so 0 2 is again 2 by 9. Okay, and then you have x1 is 1 and x2 is 0. That is again just one possibility. Okay, no, 2 possibilities. Okay, so maybe I should put a star here and a star here, right? 1 0 1 0. So you get a 2 by 9 star, and then you have 1 1 being just one possibility and 1 2 being just one possibility. I have just 1 by 9, 1 by 9. Okay, notice how the marginalization is working and how we are able to do it very easily given the table, right? That's it. It's a simple enough calculation to do. Of course, when the numbers become bigger, the probability problem becomes more complex. These things are difficult to do, but at least for simple toy problems, the basic probability, one can do this very clearly. Okay. All right. So I thought I'll put one sheet here for working, but I really don't need to work. It's clear enough what I have to do. Okay, so let's go to slightly more. So we did 2 random variables, 3 random variables. The next logical thing is 4 random variables, right? I'm just trying to show you that you can have all sorts of variety here. Again, the same principle. You sum over everything you don't want. If you want, fx1, the marginal of x1 from the joint, you sum over t2 prime, t3 prime, t4 prime. You want x1, x2, you sum over t3 prime, t4 prime. You want x2, x4, you sum over t1 prime, t3 prime, okay, from the all possibles of x1, all possibility of x3. You want the joint PMF of x1, x3, x4, right, 3 of them. Then you sum over t2 prime over x2. That's it. It's as simple as that. So from the joint PMF going to marginals is a very simple one-way process. There's multiple things don't happen there. It's very easy. Okay, but we already know from marginals you can't uniquely go to the joint PMF, and therein lies the variety in data science. Okay. All right. So let's see what. So I think that's it. I don't know. I don't think I have more worked out examples for you. That's good enough, I think. So in general, here is the general formula. I don't want to beat around this formula. You read it and understand. So if you have n different random variables, you want to take any subset of the random variables I1, I2, Ik, and want to do marginalization, you simply sum over everything except for I1, I2. So you can see start from 1, go till I1 minus 1, then jump to I1 plus 1. Go like that. Keep only Ti1 to Tik, sum over everything else, you're done, right? So that's the way to go from joint PMF to marginal PMF in the general case. Okay. So I think that concludes marginal PMF. The next big topic is conditioning with multiple random variables. That we'll do in the next lecture.